A botnet executes 5,000 checkout attempts per minute using stolen credentials against your web application. This card stuffing attack saturates your payment gateway and drives up transaction fees while degrading system performance for legitimate customers. Attackers procure large databases of stolen credit card numbers from dark web marketplaces. These lists typically contain the primary account number and expiry date, but often lack the card verification value required for final authorization. Card stuffers target guest checkout endpoints because they require less friction than logged-in accounts. Every input field on your payment page serves as a potential validation vector for an automated script testing card validity.
Bots verify cards by initiating authorizations for nominal amounts, such as $1. If the transaction succeeds, the card is marked as active and sold at a higher price for larger fraudulent purchases later. The high volume of requests triggers massive resource consumption on your web servers and database. Your application logic must handle thousands of concurrent cryptographic operations for payment encryption, which leads to significant latency spikes. Standard bots often reveal themselves through inconsistent Hypertext Transfer Protocol headers. Discrepancies between the user agent string and the supported cipher suites in the transport layer security handshake are clear indicators of automated scripts.
Analyze incoming requests for outdated or generic user agent strings. If a request claims to be a modern browser but lacks common headers like security fetch site or security fetch mode, it is likely a bot. Monitor the rate of requests from individual Internet Protocol addresses. Implementing a sliding window algorithm allows you to detect when a single source exceeds a reasonable threshold of checkout attempts within a defined period. Sophisticated attackers use residential proxy networks to rotate through thousands of clean Internet Protocol addresses. This renders simple rate limiting by address ineffective, as each request appears to originate from a different legitimate household. Use canvas fingerprinting to identify unique hardware and software configurations. By rendering a hidden graphic on the client side, you can generate a hash that identifies the device, even when the Internet Protocol address changes. Detect headless browsers by checking for specific properties like window.navigator.webdriver. Genuine user environments will have consistent screen resolution and font lists that automated headless environments often fail to emulate correctly. Stream your payment request logs to an analytics engine in real time. Visualizing the ratio of failed to successful authorizations per minute provides an immediate warning sign of an ongoing stuffing attack. Legitimate checkouts typically have high success rates. If your system suddenly experiences a 90% failure rate on credit card authorizations, it indicates that a bot is cycling through a list of invalid credentials. Avoid sending every request directly to your payment processor. Implement a pre-validation layer that checks for basic card format and bank identification number before incurring gateway costs or hitting rate limits. Utilize an in-memory data store like Redis to track request counts. A sorted set can store timestamps of requests for each user identifier, which allows for high-performance rate limiting at scale without database overhead. Set different thresholds for individual accounts versus global checkout volume. A spike across many guest accounts might indicate a distributed attack, even if no single Internet Protocol address exceeds its own specific rate limit. Incorporate response codes from card issuers into your mitigation logic. Receiving many stolen card or pickup card errors is a definitive signal of an attack and should trigger immediate blocklist updates. Assign a risk score to every transaction based on multiple factors, including geolocation and device age. Requests with a high risk score can be challenged with additional verification steps or delayed to slow down the attacker. Inspect the structure of incoming JSON payloads. Bots often use static templates that lack the subtle variations in whitespace or field ordering that are typical of requests generated by different browser versions and user interactions. Force suspicious clients to solve a cryptographic proof-of-work challenge before accepting a payment request. This introduces a computational cost that makes large-scale automated attacks economically unfeasible for the perpetrator. Deploy invisible honeypot fields that only bots can see. If an input field hidden by cascading style sheets is populated with data,
You can immediately identify and block the request as it originated from a scraper. Use invisible reCAPTCHA versions to analyze user behavior without adding friction to legitimate checkouts. Only users with low scores are prompted to complete a visual challenge, while high-quality traffic passes through seamlessly. Record mouse movement paths and click coordinates. Humans move in irregular curves with varying acceleration, while bots typically move in straight lines or teleport the cursor directly to elements, which is easy to detect. Calculate the time elapsed between keystrokes during card entry. Perfect or extremely rapid timing is a signature of script-based input, while humans exhibit natural variance and slower typing speeds on mobile or desktop keyboards. Ensure your back-end validation services are not susceptible to server-side request forgery. Attackers may attempt to bypass security layers by tricking your internal services into validating credit cards through unmonitored internal routes. Tune your web application firewall to block known bot signatures and data center internet protocol ranges. Regularly update your rule sets to include the latest patterns identified by global threat intelligence feeds from your security provider. Respond to detected bot requests with deceptive status codes. Instead of a standard error, you might return a success code, but without actually processing the payment, which wastes the attacker's time and resources. Monitor the prevalence of virtual or disposable cards in your checkout flow. While legitimate, these are often used by attackers to test gateway limits because they can be generated and discarded rapidly in large numbers. Watch for sudden increases in cards originating from the same bank identification number. A surge from a single issuer located in a high-risk region is a strong indicator of a coordinated credential stuffing campaign. Participate in threat-sharing networks to identify attack patterns seen across multiple merchants. Attackers often reuse the same bot infrastructure and stolen lists across various e-commerce sites simultaneously to maximize their reach. Never log full credit card numbers or sensitive data during a stuffing attack. Excessive logging can not only lead to security compliance violations, but also exhaust database storage during high-volume bot events. Offload your validation logic to asynchronous worker queues. This prevents your main application thread from blocking on slow external payment gateway calls and keeps your site responsive for real users, even under heavy attack. Perform local validation of card numbers using the Loon algorithm before making any network calls. Rejecting obviously malformed numbers locally saves significant resources and reduces the volume of traffic reaching your payment processor. Use client-side tokenization to ensure your servers never touch raw card data. This reduces your security surface area and prevents attackers from scraping valid credentials if they manage to compromise your back-end infrastructure. Attackers often have the card number, but guess the expiry and verification value. Monitor for sequences where the same account number is submitted multiple times with varying dates or codes, as this indicates a brute force attempt. High rates of fraudulent attempts can lead to your merchant account being placed on a high-risk list by card networks. This results in higher processing fees and a higher likelihood of legitimate transactions being declined. Successful card stuffing leads to unauthorized charges and subsequent chargebacks. Each chargeback incurs a fee and consumes administrative time for your finance team to investigate and resolve with the acquiring bank. Avoid over-aggressive blocking that impacts legitimate shoppers. Implement dynamic security levels that only escalate when specific risk indicators are met, ensuring a frictionless experience for your most valuable and trusted customers. Adjust your defense posture automatically based on current attack levels. During a suspected stuffing event, you can temporarily lower your thresholds for rate limiting and increase the complexity of cryptographic challenges for all non-logged-in users. Create clear playbooks for your operations team to follow during an attack. Predefined steps for rotating secret keys, updating firewall rules, and notifying payment partners ensure a rapid and coordinated response to mitigate damage. Log every header associated with suspicious requests for post-incident analysis. This data is invaluable for training machine learning models to recognize evolving bot behaviors and for refining your future web application firewall rules. Implement a strict content security policy to prevent unauthorized scripts from executing on your checkout page.
This prevents malicious third-party scripts from capturing card data entered by users or manipulating the payment flow. Communicate with your analytics and marketing providers during attacks. High volumes of bot traffic can skew your business metrics and lead to wasted marketing spend if you are paying for traffic that is entirely automated. Regularly test your defenses using red team exercises that simulate card stuffing attacks. Proactively identifying weaknesses in your rate limiting and detection logic allows you to patch vulnerabilities before they are exploited by real-world attackers. Card stuffing mitigation is an ongoing process of monitoring and adaptation. By implementing a multi-layered defense strategy involving behavioral analysis and robust infrastructure, you can protect your revenue and maintain the trust of your customers.